Hello, welcome to another video. So today we're trying to maximize heat transfer over a rectangular flat plate of a fixed area. So to do this, we're going to use Nusselt's number, which is, NU. This is going to be in the x direction. And this is for convective heat transfer over a flat plate with laminar flow. So this is going to be equal to 0.332 times the Reynolds number in the x direction raised to the 1/2 power, and then times Reynolds number to the 1/3. And then this we said was over a rectangular flat plate. So we can draw that. Okay. There we go. So fluid is going to flow this way. This is going to be the x direction. This can be y. And then back here, this can be z. And this is a length in the x direction. And we're going to have a boundary layer here. As well. Okay, so I'm going to move this out of the way. Okay, so Nusselt's number is just a ratio between convective and conductive heat transfer. This is conductive. And actually, oops. Okay. And so this is going to be equal to, oops, I spelled that wrong. There we go. So the convective heat transfer coefficient is H, and the conductive heat transfer coefficient is K. And because this is on a flat plane with a fixed area, we said that this length here is x, so we're going to multiply this by x. And then, so there's that. Then we have Reynolds number. That is the density times length times velocity over viscosity. And then this length, we can just say that it's x to keep things consistent, like we did up here. Okay, and now we have Reynolds number. This is going to be a ratio of momentum diffusivity over thermal diffusivity. Okay, and that's going to be viscosity over density, and that's going to be over the thermal conductivity over heat capacity times density. And so when we simplify this, it's going to be viscosity times heat capacity over thermal conductivity. Okay, so we can plug these values in for the Nusselt number, Reynolds number, and Reynolds number in this equation up here. So we have our convective heat transfer coefficient times the length over the thermal conductivity going to be equal to 0.332 times the Reynolds number we said is density times velocity times length over the viscosity. This is the 1/2. And then Reynolds number we said was viscosity. Viscosity times the heat capacity over the thermal conductivity. This was to the 1/3 power. Okay, so if we remember at the beginning of the video that we're trying to maximize heat transfer, and we're using convective heat transfer equation. And so if we're looking at where convective heat transfer takes place, it's in the numerator of Nusselt's number. So we're trying to focus on this H, or the heat transfer coefficient for convective heat transfer. So we want H to be on its own. So it's going to be H, or the heat transfer convective heat transfer coefficient is going to be equal to 0.332 times density times velocity times the length over viscosity to the 1/2 times viscosity times heat capacity over thermal conductivity to the 1/3 times thermal conductivity over the length. Okay, and then now we can simplify and we get this finalized equation where the convective heat transfer coefficient is going to be equal to 0.332 times density times velocity over viscosity to the 1/2 power times viscosity times heat capacity to the 1/3 times the thermal conductivity to the 2/3, and the length is going to be to the negative 1/2 power. Okay, so we're trying to maximize heat transfer, right? So I'll move this up by the picture here. Okay. Okay, so we want H to increase. And if we're looking here at the equation, the thermal conductivity is like per what the surface is, so that's not going to change. Same with the heat capacity. If it's going to be one fluid, we won't be changing the viscosity of it or the density of it necessarily, so those don't really impact the heat transfer. We can look at the velocity or we can look at the length. So we could increase the velocity to make heat transfer increase, or we're really going to focus on the length. So if you increase the length, this will get smaller because this negative 1/2 is just the square root of x in the denominator. So increasing that would make the h term be smaller. So as x increases, h decreases. So if we want h to increase, we have to make x smaller. So that means increasing the length along the z-axis, or where the fluid like first makes contact with the surface. And that's how you can maximize heat transfer on a flat plane, rectangular plane.